Welcome to this lesson on linear inequalities and systems of inequalities in two variables. Understanding linear inequalities is crucial in many fields, including economics, engineering, and computer science. In today's video, we'll explore several examples to help you visualize and solve these types of problems. For each example, we'll follow a three-step process. First, we'll write the inequality in standard form. Second, we'll sketch its solution region in the xy plane. And for systems of inequalities, we'll find the overlap of the individual regions. Let's start with single linear inequalities. For our first example, we'll work with the inequality 2x plus 3y is less than or equal to 6. Step 1. Let's rewrite this inequality in slope-intercept form, which is y equals mx plus b. Starting with 2x plus 3y is less than or equal to 6, we subtract 2x from both sides to get 3y is less than or equal to negative 2x plus 6. Then we divide everything by 3, giving us y is less than or equal to negative 2/3 x plus 2. Step 2. Now we'll graph the boundary line, y equals negative 2/3 x plus 2. This line has a slope of negative 2/3 and a y-intercept of 2. Since our inequality includes equality, they are equal to part, we draw this as a solid line. Step 3. To determine which side of the line to shade, we'll use a test point. Let's choose the origin 0, 0. We substitute this point into our original inequality. 2 times 0 plus 3 times 0 equals 0. Is 0 less than or equal to 6? Yes, that's true. So we shade the side of the line that contains the point 0, 0, which is below the line. Let's move on to our second example. Here we have the inequality x minus y is greater than 1. Step 1. Let's rewrite this in slope-intercept form. Starting with x minus y is greater than 1, we subtract x from both sides to get negative y is greater than 1 minus x. Then we multiply everything by negative 1, which flips the inequality sign, giving us y is less than x minus 1. Step 2. Now we'll graph the boundary line, y equals x minus 1. This line has a slope of 1 and a y-intercept of negative 1. Since our inequality is strict greater than, not greater than or equal to, we draw this as a dashed line. Step 3. Let's use the test point 0, 0 again. We substitute this point into our slope-intercept form inequality. Is 0 less than 0 minus 1, which is negative 1? Yes, that's true. So we shade the side of the line below it, which contains the point 0, 0. Now, let's move on to systems of inequalities. A system of inequalities consists of two or more inequalities that must be satisfied simultaneously. The solution is the region where all individual solution regions overlap. For our third example, we'll work with this system. Y is greater than or equal to 2x minus 1, and y is less than negative 1/2 x plus 2. Step 1. Both inequalities are already in slope-intercept form, so we can proceed directly to graphing them. The first boundary line is y equals 2x minus 1. This is a solid line because the inequality allows equality. The second boundary line is y equals negative 1/2 x plus 2. This is a dashed line because the inequality is strict. Step 2. Now we need to determine which side of each line to shade. For the first inequality, y is greater than or equal to 2x minus 1. Let's test the point 0, 0. Is 0 greater than or equal to negative 1? Yes, that's true. So we shade above this line. For the second inequality, y is less than negative 1/2 x plus 2, using the same test point 0, 0. Is 0 less than 2? Yes, that's true. So we shade below this line. Step 3. The solution to the system is the intersection of these two shaded regions, shown here in purple. Let's look at one more example of a system of inequalities. Here's our system. 2x plus y is less than or equal to 4, and x minus 2y is greater than or equal to negative 2. Step 1. Let's rewrite both inequalities in slope-intercept form. For the first inequality, 2x plus y is less than or equal to 4, we subtract 2x from both sides to get y is less than or equal to negative 2x plus 4. For the second inequality, x minus 2y is greater than or equal to negative 2, we subtract x from both sides to get negative 2y is greater than or equal to negative x minus 2. Then we divide everything by negative 2, which flips the inequality sign, giving us y is less than or equal to x divided by 2 plus 1. Step 2. Now we'll graph both boundary lines. The first boundary line is y equals negative 2x plus 4. This is a solid line because the inequality allows equality. The second boundary line is y equals x divided by 2 plus 1. This is also a solid line because the inequality allows equality. Step 3. Now we need to determine which side of each line to shade. For the first inequality, y is less than or equal to negative 2x plus 4. Let's test the point 0, 0. Is 0 less than or equal to 4? Yes, that's true. So we shade below this line. For the second inequality, y is less than or equal to x divided by 2 plus 1, using the same test point. Is 0 less than or equal to 1? Yes, that's true. So we also shade below this line. The solution to the system is the intersection of these two shaded regions, shown here in purple. Let's summarize what we've learned about linear inequalities and systems. To solve a linear inequality in two variables, 1. Rewrite it in the form y is less than or equal to mx plus b, or y is greater than or equal to mx plus b. 2. Draw the boundary line, y equals mx plus b, making it solid for less than or equal to or greater than or equal to, and dashed for strict inequalities. 3. Test a point not on the line, usually the origin, to determine which side to shade. For a system of inequalities, 1. Solve each inequality separately. 2. The solution is the region where all shaded regions overlap. Thank you for watching. I hope this video has helped you understand linear inequalities and systems in two variables.